Hello everyone, welcome back to my channel, and in today's video we're going to solve some AITS problems. So let's begin with the first problem. So this is based on gravitation. So we have a thin tunnel that is made in a planet of spherical shape. Radius is r, acceleration due to gravity is g. A block of negligible mass is pushed into the tunnel at the mouth of the tunnel at end A. So the surface of the tunnel is actually rough and the coefficient of friction is given to be mu. So we have to figure out the maximum speed of the block through the consequent motion. Okay, so give this a try guys and then check out the solution. Okay guys, so the ball is left somewhere over here. So basically the force on the ball is going to be towards the center of the planet, and we also know the result and the result for the value of g. So the value of g at a point whose distance from the center is r is actually gm r vector divided by r cubed. So it is linearly proportional to the distance, right? So inside the planet, as we move radially outwards, the g field varies linearly with the distance. As we are dealing with points that are within the sphere, we're going to use this formula. The force on this mass is going to be m into g. So now if you observe the motion of this particle over here, it is going to move along the tunnel, right? So let's just mark that direction as the x direction. So let's just call this angle as theta. So, and let's say this is our mass. So the forces on it are, first of all, there is going to be a component of mg, which is going to be mg sine theta. And then there is going to be an mg cos theta in the downward direction, which is going to be balanced by the normal reaction from the tunnel. And then there is going to be friction from the bottom surface of the tunnel, right? So now as the ball is slipping relative to the tunnel, we can say the friction is kinetic in nature. So we can simply write this mu times n, which is mu mg cos theta. So now let's write down the equation of motion in the x direction. So we can say mx double dot equals mg sine theta minus mu mg cos theta. So from here, this is the expression for the acceleration that we're getting. So as we can see that theta is decreasing as the motion progresses, which means sine theta will go down and cos theta will go up. So initially, obviously, the ball is going to get accelerated, but as we can see, the acceleration decreases as time progresses, and at some instant when the acceleration is going to become 0. That happens when sine theta equals mu cos theta, or basically when tan theta equals mu. And after this particular point, the ball is going to be decelerated. So now as we have to find the point where the velocity is maximum, that corresponds to this particular point where the acceleration becomes 0, because till that point the ball is accelerating and after that it starts decelerating. So now the value of mu is given to be root 3 by 2. So now this distance is r by 2. So let's say that specific point where the acceleration becomes 0 is at a distance of x star from the center of the tunnel. So now we can use trigonometry and figure out x star. So x star divided by r by 2 is tan theta, which is root 3 by 2. So x star comes out to be root 3 r by 4. So now we can proceed by two approaches. So either you can use energy conservation or you can use this equation of motion over here. So the acceleration, I can write it as v dv upon dx, and dx I'm going to send it to the other side. So this is going to be g times. So let's write down the value of g. So gm r by capital R cube, and where r is this particular distance that connects the center to our particle, right? This multiplied by sine theta minus mu cos theta. Now what I'm going to do is send this r into the bracket, and this will become gm by r cube multiplied by, now r sine theta from this triangle is this particular distance. In fact, instead of considering x from the right end, we'll just consider x from this end over here, because everything is being measured with this x, right? So the only thing that will change is that now the acceleration will become negative. We need to put a minus sign over here, because why? Because the value of x is decreasing, right? So this will become minus gm by r cube times r sine theta is x. R cos theta from this triangle is nothing but r by 2, and it's a constant, right? So this becomes mu times r by, so now we can integrate on both sides. So initially the value of x is this particular distance over here. So this distance is, so let's figure it out. So this is r and this is r by 2. So this distance over here, so the initial x distance is going to be square root of r square minus r square by 4, which is root 3 r by, so the initial limits of x is root 3 r by 2. And the final limit is going to be root 3 r by 4, which was x star that we just calculated over here. And after solving, we will get v square as 3gm by 16r. Now we know g at the surface of the planet is gm by r squared. So gm, we can write it as gr squared. So the velocity just comes out to be root 3gr divided by 4. So now let's move on to the next question. So in this question, we have a cylinder whose mass, height and radius are given. When it is put in water, it floats with half of its volume submerged. So this condition is essentially given to figure out the density of the cylinder. By using the condition of buoyancy, we can say the density of fluid times the volume submerged into G would be equal to density of the object times its volume times G. So now as it is given that it floats half submerged, so the submerged volume is going to be V by 2, which essentially implies that the density of the object is half the density of the fluid. Okay, so that's what, so that was the purpose of the first sentence. So then they have mentioned the cylinder is placed in the cylindrical vessel of inner radius 2r, which is double the radius of the cylinder, and on a spring whose force constant K is given, such that the cylinder is inside the water by h by 3. So now 1/3 of the volume is actually submerged in the presence of the spring. In this case, we have to figure out the minimum energy required to push the cylinder such that it is completely immersed in water. Okay, so when they mean minimum energy, it essentially means that we are doing it in such a way that the cylinder does not accelerate. So it's just the potential energy change between the initial and the final stages. Okay, so first let's write down the equilibrium condition. So let's assume the initial compression in the spring to be some xi. So the spring force on the cylinder is going to be K times xi, and obviously we have the weight of the cylinder mg, and then we have the buoyant force. With the buoyant force, we can actually do something neat. The volume submerged is actually 1/3, right? And the density of the fluid is double the density of the water. So the buoyant force is actually 2 by 3 mg, right? Once again, it's because 1 by 3 comes because 1/3 the volume is submerged, and 2 comes because the density of the fluid is double the density of the water. So from here we get kx1 as mg by 3. So if you substitute the value of K over here, you'll get the submerged value as h divided by. So now we figured out the initial compression in the spring. Okay guys, so now the next important thing is that if we try to push this cylinder in by an amount, then the thing is the water level is going to go up because of volume conservation. And that is what we have to figure out. So let's say we physically displace the top of the cylinder by a small distance x. So let's say this is our spring. So if I physically displace the cylinder by an amount of x, the spring is going to get compressed by an amount of x. And let's say as a result, the water level goes up by an amount of y. So we can easily figure this out. So if I push this in by an amount of x, so this is the new volume that is taken up by the cylinder. So that volume, let's call it V, we can easily write it as x multiplied by the area of cross section of the cylinder, which is pi r squared, right? So this is exactly the volume of the fluid that is going to rise. And the fluid that was initially present over there will actually come over here as a result of the height increase. So, and the volume of increase of the fluid. So if you look at it from the top, the surface of the fluid will appear as a disk with a hole in the middle. So the volume in this case I can write as y multiplied by pi into 2r squared minus pi into r squared, which is 3 pi r squared y. So now these two volumes have to be equal. So from here we get that y equals x by 3. So what that means is that if we push the cylinder in by an amount of x, the water level rises up by a factor of 1/3 of that value. So finally what we want is that we want the cylinder to be completely underwater. So, and we know that outside of the water, initially 2h by 3 height of the cylinder is present. So let's say we push the cylinder in by an amount of x. The water level is going to go up by an amount of x by 3, and we want these two to together add up to 2h by 3 so that the entire cylinder to be completely underwater. And this would be equal to 2h by 3 implies x equals h by 2. So if we push the cylinder in by an amount of h by 2, then what happens is the cylinder is now completely submerged. Something like this. Okay. Okay, so now we have to talk about the potential energy changes. So now the change in spring potential energy is pretty easy. So the delta PE of the spring, half k times x final squared, and x final is nothing but xi plus h by 2. And why is it h by 2? Because we pushed the cylinder in by an amount of x, right? So which means the spring gets compressed by an amount of x, and x is nothing but h by 2. This thing squared minus half k xi squared. So change in spring potential energy, we figured it out. Next we have to talk about the change in the potential energy, gravitational potential energy of the cylinder. And that's also pretty easy to understand because we just pushed the cylinder in by an amount of h by 2. So its potential energy actually decreases. So this just becomes minus mg times h by 2, right? And now we have to determine the change in the gravitational potential energy of water. So this is the slightly tricky part. So for this, what we can do is imagine the water surface without the cylinder present. So this is how the surface of the fluid looked in the initial case. So this height was equal to h by 3. And for the final case, I am choosing a different color. Now this point over here, guys, this is where the base of the cylinder was actually present, right? And we know that this point will move down by an amount of x because we pushed the cylinder by an amount of x. So the new base of the water will be over here, which I drew with the dark green line. So basically the mass that was initially present over here, mass of the water, gets deleted basically, and now that becomes empty space. So this distance is x, this distance is h by 3. So, and now what will happen is the mass that was initially present over here will come over here, right? So I'm going to draw it something like this, and in between this thing the cylinder is present. And if you guys remember, this height over here was x by 3, right? Okay, so now as we just want the change in the potential energy of fluid, we can just observe this mass over here, because the potential energy of this mass is the only thing that's changing. So I'm going to mark the center of mass with yellow color. This is where the center of mass was initially present, and finally it's over here, right? So the delta y, so now let's figure out the delta y. This distance is x by 2, this distance is h by 3, and this distance is x by 6. Right, basically half of x by 3. So the change delta y, so I'm going to write x as h by 2. So this is going to be h by 4 plus h by 3 plus h by 12, which comes out to be 2h by 3. So now we can write down the PE of water pretty easily. So that will be equal to the mass of this much water, which is nothing but, so the volume of that much part of the water is pi r squared x, and x is nothing but h by 2, and this multiplied by the density of the fluid, which I can write it as twice the density of the object. So the 2's cancel out, and pi r square h sigma is nothing but the mass of the cylinder. So this is nothing but m g times the delta y, which is 2h by 3. So this is the change in potential energy of water. So now let's use work energy theorem. So according to that, we can say that the change in potential energy of the system is nothing but the work done by the external agent. So now we can just add up all the change in potential energies. So now we can use a square minus b square formula over here. And after solving, you will get the answer as mgh by 12 root 3 plus, which was option B. So now let's move on to the last question. So this is the last question, and this question is based on radiative heat transfer, and this is a very nice problem. So in this question, we have a solid cylinder and a hemisphere as a combined system, and it's given that the cylinder over here is painted with shiny white. Essentially what that means is it's a purely reflecting surface, and it does not absorb or emit radiation. And this hemisphere is painted dark black, meaning it can be treated as a black body. So it essentially it's a good emitter and absorber of radiation. The initial temperature of the body is given to be 300 Kelvin, and it is released from rest in a gravity free space where the temperature of the surrounding is 0 Kelvin. Okay, so the surrounding temperature is 0, and the body attains some terminal velocity according to them. So what they're claiming is that obviously there is going to be some radiative heat transfer because there is a temperature difference, and finally when both of the temperatures become equal, right, the surrounding temperature and the temperature of the body become 0 Kelvin, there is some velocity. The combined body actually moves with some velocity, which they're calling as V0. The graph of the specific heat of the solid and the temperature of the body is given as this particular function over here, and we have to determine the total heat energy. So the total energy basically in kilojoules radiated by the body, also the terminal velocity V0 of the body. Okay guys, so as I discussed earlier, the white surface is a poor emitter and absorber, so we can approximate it to not emit any radiation. So only our hemisphere over here emits radiation. dq by dt, which I'm going to call as q dot, is the heat that is leaving the body. And this I can write it as sigma, which is a Stefan's constant. E is E, we can just consider it, the hemisphere, as a black body, so we'll take it as 1. So the area through which radiation is emitted, which is 2 pi r squared times t power 4 minus t naught power 4. The surrounding temperature is 0 Kelvin, so this is just going to be t power 4. Okay, so this is what the radiative heat transfer from the hemisphere is coming out to be. So let's say if the body loses a heat dq to the surroundings, then I can also write dq as ms dt. So if it loses or gains an amount of dq, then its temperature increases by dt, and they can be related using this relation. From here, we can also figure out something. If I integrate this expression on both sides, then I can figure out the total heat transfer between the initial and final stages by just integrating this expression of s dt. And integral of s dt, if you guys observe, is just the area under this curve. Find the area under the curve, it comes out to be 70 kilojoules per kilogram. Mass of the solid is given to be 1 by 3 kg. So q, this comes out to be 1 by 3 multiplied by 70, which is nothing but 23.33 kilojoules. So this would be the answer to the first problem. That is the total energy radiated by the body. Okay, so now let's talk about the terminal velocity part. Okay guys, so for the terminal velocity part, so why is the body acquiring a velocity in the first place? And the answer is, it is because of radiation pressure, or you can simply say that as the surface is emitting radiation in all direction, if you consider the emitted radiation as packets of photon, so there is a momentum generation over here, right? The photon is actually acquiring some momentum in this particular direction, that is basically in the radial direction, which means there was a force applied on the photon in this direction. So the photon will apply a force on the surface in the opposite direction. This is the direction in which radiation is emitted. So the force by symmetry, we can see that it will be towards the left. And so because of the emission of radiation, there will be some force that is applied on this body, which is going to move the body. So now let's try to figure out the magnitude. So if I just consider a dA element on the surface of this hemisphere, and again guys, we don't have to bother about the cylinder over here because it does not emit any radiation. So there won't be any forces associated with the cylinder. And let's say the radiative heat transfer from this small element dA is dq dot. dq dot I can easily write using the idea of solid angle. So q dot heat is transferred through a solid angle of 2 pi steradians, right? As heat is being emitted throughout the hemisphere in all directions symmetrically. So q dot radiative heat transfer is being radiated through a solid angle of 2 pi steradians. So what is the solid angle of this small patch dA on the surface? So this distance from the center of the hemisphere is r. So we know that the solid angle subtended by the small element dA is dA divided by r squared. So if I multiply dA divided by r square over here, I'll get the dq dot. So this is basically the solid angle, and this term over here you could say is the heat transfer rate per unit solid angle. So we now figured out the rate at which heat is radiated by this small dA element. So now guys, I am going to link a video in description. So in that video I covered almost all the cases of radiation pressure. So I'm just going to briefly cover it over here. So if I have a surface over here which is inclined, let's say at an angle of theta with a vertical, and let's say a radiation of intensity I is incoming in the horizontal direction. So the incident power on this surface actually comes out to be IA cos theta. So you can kind of get a feel by imagining this rod to be horizontal. In this case, no power would be incident on it, right? And this is also the case where the angle with the vertical is 90 degree. So again, in the perfectly absorbing case, which is the case that we are discussing currently. So in that video, I discussed that in the perfectly absorbing surface case, the momentum individual photons are completely destroyed after it hits the surface, right? So if I imagine a photon over here, so some force F is applied on the photon to bring it to rest after colliding with the surface. So it basically means there is some force that was applied on the surface in the opposite direction. So in this case of the perfectly absorbing surface, the force actually comes out to be in the same direction as the incoming light intensity. Now, this case over here is exactly identical to this case. The only difference is that intensity is leaving the surface, right? But if you imagine a photon particle over here, its momentum is in this direction. There must have been a force on this photon in the radial direction, which means a photon must have applied a radial force, a force on the hemisphere in the opposite direction. So essentially in this particular case, the force is in the minus r cap direction. So opposite the radius vector. So let's call the force as df. Okay. Now what is the magnitude of this force F? So this actually I covered in that video. The force that acts on the surface comes out to be P divided by C, where P is the incoming power received by the surface, and P we can also write it as IA cos theta divided by C. So do watch that video out for better understanding of this topic, guys. So here we decided on the direction of the force F on the, so now what we can do is, and so the magnitude of the force F, it is equal to the power transmitted, which is dq dot in this case, right, divided by C. So now let's say this element makes an angle of theta with the symmetry axis of the hemisphere. So if you take a symmetrical element at an angle of minus theta, so on this patch, the force is going to be df in this direction. So as you can see, the vertical components just symmetrically cancel out, and only component that remains is the horizontal component. So the net force is as good as integrating the horizontal component of df, which is df cos theta. Q dot divided by 2 pi r squared C times dA cos theta and the integration of this, because everything else is a constant. Because q dot is a constant with respect to theta, right? It does change with time, but it's not changing with respect to theta. So we can take it out of the integral. Now the integral dA cos theta is nothing but the projection area of this hemisphere in the vertical plane, and that is nothing but pi r squared. So the final expression for the force is q dot divided by 2 pi r squared C multiplied by pi r squared. And this comes out to be q dot divided by 2c. So this, as you guys can see, it's going to be a time dependent force, because q dot, as we discussed earlier, it is going to change with time, right? Because the temperature, as the temperature of the body goes down, q dot actually becomes lesser and lesser in magnitude. So q dot is clearly depending on time, right? But we don't care about that because we don't want the exact function of the force, right? All we want is a terminal velocity. In order to figure that, we can use the impulse momentum theorem. So basically we can write the integral of f dt, the net force dt, would be equal to the change in momentum. So which is m times the terminal velocity, which let's call it. From here, we get Vt as 1 by m. Now guys, integral f dt is going to be 1 by 2c times integral of q dot dt. So integral of q dot dt is nothing but the net. So it's the net heat energy that is transferred in between state 1 to state 2. So which we actually figured out in the option A, right? So this actually becomes, so the final answer becomes q divided by 2mc. So which after solving comes out to be 0.117 millimeters per second. Okay, so that was it for this video guys. If you enjoyed the video, do like, share and subscribe to my channel. And that's it. Thanks for watching.